Hello, my name is Adrian Jensen with Predictive Engineering and Applied CAX, and today's seminar is going to be about advanced post-processing in Femap. I'm going to be using version 11.2.2, and we're going to talk about a variety of subjects. A little bit of an outline here. We're going to start out with file management. Now, this isn't the most exciting topic for post-processing, but it's very important, especially when you're working with very large data sets. So you either have large models or you have nonlinear analysis that's giving you multiple output sets for each analysis run. So we're going to take a look at the preferences, see where those files are stored, see what type of information is stored in those files, and also see how we access those files with our Femap model. Moving on, we'll use the post-processing toolbox, work through some standard stuff like deformed views, contoured views, and then we're going to spend some time on the free body diagrams. Moving on to the data table. This is a great tool for tabular data. You can list a bunch of nodes and elements and displacements, forces, stresses, all in a tabular form. It exports to Excel nicely, makes nice tables for your engineering reports. And then we'll be wrapping up with some Femap APIs. So I've got 3 APIs to look at. They're kind of simple APIs, but I think they're really useful, and it should open up the door for you guys to explore post-processing with some automation and some programming down the road. Okay, so we're going to get started, and we're going to open things up in the preferences of Femap. And the first thing I want to look at is where we direct our output to. So we're going to look where our scratch files go and where our output files go. So as Nastran is running, it's generating temporary files. And our preferred options here is to direct the scratch and the output to a scratch directory. You're going to want to set that folder up on your local drive, not on a network, and preferably on the fastest drive on your machine. So if you have a solid state drive, that's going to help speed up analysis times because you'll be reading and writing from that local drive that's very fast. Femap itself is also going to generate scratch files, so that's another one of our defaults is we'll make sure that our Femap temporary files also end up in that scratch directory. Now this is really nice because you know exactly where to look for your output files, and also at the end of the month if you need to clean up some free space on your machine, you know exactly where to go. You're not going to have output files sprinkled throughout all these different directories on your machine or across a network. Okay, so let's go ahead and open up Femap and take a look at these preferences here. So File, Preferences, you want to go to the Interfaces tab. Be aware that there's an Interfaces and a User Interface tab, so we want Interfaces. And here we go. Option number 2 for both of these, and then that scratch folder there on my C drive. Okay, next we're going to talk about the actual files that get generated by an analysis run, by Nastran. So the default here is to print all of your post-processing information, your forces, your stresses, and your displacements to the OP2 file. And you can see on the last page of your analysis manager here, the results destination. You have a variety of options. So the default is post-process only. So it'll generate an F06 file that will give you some information about your loads, your constraints, any errors that the model might be having during analysis. And it also generates an OP2 file. Now the OP2 file is where all of your forces, stresses, and displacements are stored. And it's not an ASCII file, so you can't open it with a text editor. So if you have the need to open up and see these displacements, forces, and stresses in a text editor, you're going to want to switch to option 3, print and post-process. This is going to print these values to the F06 file, which you can open up in a text editor. So let's take a look here. I'm going to open up my scratch directory. So I've got my computer here, C drive, And there's my scratch file. So I've got a model, and I ran this model with both option 2, post-process only, and option 3, which is print and post-process. So option 2, if you take a look at the f06 file, it's quite small, 42K. For the one I ran with post and print, you can see the f06 file is quite large, about 61 megs. So let's take a look at these files. So this one is fairly short, a little information about the solver, some good information for the analyst to check in here, I would say, is the O load, get your total input load to your model, and your SPC force resultant, how much reaction force your constraints are seeing. But once you scroll down, if there's no errors in your analysis, that's all you get. Now let's look at the one that I used print and post-process, this large file here. All of the same information at the start, but once we really start to scroll down into the meat of it here, we've got displacement vectors, we've got forces and quadrilateral elements, stresses and solid elements. All of your post-processing information is printed here. You can copy it, paste it into the report, put it in a table. It gives you access to this raw data. You don't actually have to bring it in to Femap to post-process. You can just have the raw numbers right here. The downside to this is file size. You can see we're taking up a lot more space printing to the f06 file. All right. Next, I want to talk about attaching to results. So once we've chosen where our output files are going to go and where our output data is going to be stored within those files, we get to choose how Femap handles those files. So the default is to internalize those results. Once the analysis runs, it's going to import those results into your Femap model, and when you save your Femap model, that will be internalized. So you can kind of see the visual here. Here's our Femap model. Here's our results. This would symbolize our OP2 file. And when you import all those results, you get a little bit of, this is memory here, a little bit of blue for overhead, managing those files. And then all of that file size of the results increases the file size of your model. So if you've got 6 gigabytes of output data, your model file is going to grow at least 6 gigabytes in size. Now this can really slow things down. Importing this data is slow. Saving and opening large models like this can be slow. So the alternative is attaching to results files. Rather than automatically importing those into your Femap model file, you can choose to attach. And this keeps it separate. So you'll have your model file, your .modfem, and you'll have your output file, your .op2. And you need to make sure that you keep both of those files. So it opens quicker, it saves quicker, runs quicker, but the downside is now you have 2 files to manage. So let's take a look at this in Femap. I've got a large model here. It's about 800,000 nodes. And we had run several individual load cases and then a multi-set load case that gave us several output sets. And I don't have those results internalized here, but I do have the OP2 files. So the classic way of doing it would be importing your analysis results. This what happens automatically when the analysis runs is complete. You can do it manually like this. I would choose an output file, and you can see I can only choose one at a time. And it's working its way through the import here. It'll do a little bit of cleanup. And in a few seconds here, we'll have an output file. And that'll become a part of my model file. So my model file is going to grow in size. And you can see that here. Now to attach to results, it's a little bit different. Rather than file import, I want to move down to the next item, which is attach to results. This brings up a little toolbox here that helps you manage your results files. and we are going to choose to attach files. The nice thing about this is you can also do multiple files at one time. So that last one is about a half a gigabyte here. You can see I have other files about that same size, and then this multi-set output, which is about 4 gigabytes here. So I'm going to attach all of these, and the nice thing about this is it not only keeps your model file size a bit smaller, it attaches quite quickly. So it's going to work through these output sets, and then it's going to list them all together here in this output manager. Now once they are attached, I can choose to just simply leave it at that. It's not really going to increase my model file size. Or I can choose to internalize certain results. You can internalize an entire result set like I did with the import command, or the really nice thing is you can choose to internalize just a portion of the output set. So if you look in the model info tree, here's the one that I had imported, and these ones here are attached. You notice there's a little different logo. So let's internalize some of these results, and we'll just do a subset. So I'm going to select my output file. You can see it's got a file path here. And I'm going to say save to model. The nice thing about this is you can choose exactly what portion of the output set you want to save to your model. So I'll choose this output set. Say you're just interested in translation and maybe our solid von Mises stress. So let's find solid von Mises. Okay. The other thing I can do is rather than for my entire model, I can just use a portion of the model. There's already been some groups created in this model here, so I'm just going to choose one group here, and I'm just going to limit my import to the nodes and elements in that group. And there we are, we're all done. So we can click done. You can see that one has the same little icon as my imported analysis results up top here. Let's activate this, and within the post-processing toolbox, I'm going to deform and contour. So you can see the only part of my model that's deformed or contoured is just what's in that group there. So we take a look at that group, and there we go. We have deformed and contoured data for just that small subset of the model. So if you do need to internalize results, but you're still worried about the model file getting too large, you can use this attach to just bring in part of it. All right, so attaching, if you've have results files already that you want to attach, you can see the attach manager here. But you can set it up in preferences to choose how this is going to work. So here's the defaults here. It doesn't automatically attach to results. So if this is the method you want to use, as soon as an analysis is done, you want it to automatically attach to those results files rather than importing, you can turn that on. The other option here is mapped memory files. So what this will do is this will actually import all those results files, but it'll store them in the RAM. So as long as you have enough RAM to store all of that output, it's going to be stored there, and it's going to run a bit quicker. If you don't have enough memory to store all of that data, it's just going to treat it like it normally does, reading and writing from the drive. Okay, the next topic, conveniently, is right here, create studies. Creating studies is just a simple way to organize your results files in the model info tree. So you'll notice on maybe starting with version 11.2 that there's not just results, but there's analysis studies. And these are really just folders, ways of storing multiple output sets grouped together. So I have my default to automatically create studies. I'm going to go ahead and turn this off for now. I usually only turn this on when I'm working with really large models. It's not my default setting. Let's open up a different model file here. I've got this one here. There we go. Now this is set up. I've got 3 load sets, 1 constraint set, and you can see I've run several different iterations here. And since I had create studies turned on, every time I hit the analyze button, when the results come in, they're stored within a study. So you can see here's my first 3 runs. Then I'd modified one of the properties or thicknesses of my model and ran it again, and it gets stored here. So this is a really nice way to organize your results. It also kind of cuts down on having to give really detailed names. So you can see in my example here I have updated thickness, and then in the 3rd round of analysis I'd altered the constraints. So if you just have a long list of output sets here, the output set titles don't really give you all the information you want to know unless you rename them. So you can use analysis studies, just rename the top of the study, and have those groups of 3 or 10 or however many output sets you have clustered together. Nonlinear analysis is another one where I think this comes in really handy. You might have 10, 20, 100 output sets for a single nonlinear run. You want those grouped together, letting you know, all right, these all sit with one specific analysis. The next 10 or 20 sit with the next analysis. So it's a simple tool, just provides you with a little flexibility in organizing your output. All right, so that's our file management section there. Obviously, there's a lot of information there. You kind of have to get some experience with the large models to see if this is really going to help you out or maybe cause hassle, but you know where the clicks are now. Up next is our post-processing toolbox. So Femap always has multiple ways to access every command or every feature, and as time has progressed, more and more of the post-processing tools have been consolidated into this toolbox. So we're going to take a quick look. I've got this model here. I've already got results. So maybe from the model info tree, I'll just double click and activate one of those results. You can see activate an output set. And then from the post-processing toolbox, we'll start at the top and we'll work our way down. So first is deform. This is pretty standard here. You can either choose to deform or animate your model. The output vector you're almost always going to want to use is the total translation. And then you can choose how to actually scale that deformation. So I like to use actual deformations and choose some sort of scale factor. You can see with this one I've got very small deflection, so I might bump it up by a factor of 100 to really see what's going on. So you can choose different output vectors. Like I said, total translation is really the one that makes sense for a deformed view. And you can also choose your different output sets here. So depending on the output set, you might need to adjust your scale factor for something that looks reasonable. There's also an animated view. And if you're working with nonlinear analysis where it's going to give you multiple output sets for a single run, you can choose a multi-set animation. What I like about the post-processing toolbox, it's got this little button right here, and that just turns off all of the post-processing. So it's very nice, a single button to turn it all off. We can move on to contour. Now contour, this is the classic post-processing image you see, the contour colors, stress contoured over your model. So we can turn on contour, and we'll choose our output set. I've got this output set 4 chosen here. And then we choose our output vectors. So the first thing I'm going to do is this model here. If I turn off my thickness, you can see most of it has been created with plate elements. So I'm going to want plate top and plate bottom stress. So there is an option here, double-sided planar contours. So when working with plate elements, I want to make sure I have my plate top and my plate bottom stresses. You can see that those two values are different there, and it might be easier to see with thickness turned on. But if you don't have that double-sided planar contour option, you're only going to be seeing one side of the plate stresses. In more recent versions of Femap, you've been able to contour multiple types of output vectors at the same time. So I've got my plate top and my plate bottom. You can see I've also got my beam stresses. I used beam elements for the pins here, and I used solid elements for this block here. So I've got beam and solid stresses. I can view all of those at the same time. I think some of the more advanced features in Contour are here under Transform. If you want to view stresses in a certain direction, not necessarily your von Mises or your principal, but you want to know what is the stress in the x direction, you can transform your stresses into a certain direction. So I'm going to turn off my additional vectors, and I'm just going to look at my plate x stress. Now this contour is not very smooth, it's a little bit blotchy, and that's because my plate x direction doesn't always align with the global x direction. If I turn on my element orientations, that'll show me my plate x direction, you can see it, these are aligned, these are perpendicular, it kind of switches around. So what we need to do is we need to transform all of these x stresses into the global x direction. Turn off my orientation, and under transform I want to transform plate stresses. We'll go to the basic rectangular and we'll choose the x direction. So you notice once I do that, it's very smooth. I've got consistent direction, and this shows me my force or my stress component in the global x direction. Another component of the contour post toolbox here is, we'll turn off our transformation here, is your data conversion, choosing how your elements average and where you're pulling that post data from. So we've got two main categories here, either centroid only, or this top here includes our corner data or our nodal data. So first of all, you get to choose, do I want one data point, my centroid stress value for each element, or do I want to choose 5 data points, my centroid and my corner data? Different element types are going to have different number of data points. These hex elements over here, they're going to have 8 data points and the centroid. The next thing I choose is how they average. So do I want to turn off elemental averaging? You can see here I have a very blocky discrete view where elements aren't averaging their stress data with their neighbors. You see if I switch to no average, centroid only, each element only has a single point of data. Or I can choose to average, choose maximum values, minimum values, and those same options for centroid only. So this average value with corner data, that's the default, and that's kind of the go-to I use, but I like to know what these other options are for, what's going on in the background, because they can be really useful depending on your scenario. We do have previous online seminars like this one that really focus in on that elemental averaging. So if this is something that interests you, I encourage that you check those out. All right, one last option here for the contour. I'm going to go, I'll turn on our translation here. You can see we've got a legend set very high, so we can't really see those. Those are all down here low. But the last one that I want to look at is our contour vectors. So we can show our stresses as contours. We can also show them as vectors. So when you switch over to contour vectors, you have to use this little pop-out toolbox here. And I usually look at something like our major principal and our minor principal stress. You can choose what color those vectors will show up as. So I usually like to do red and blue. And then just like we transformed our x stresses into the global coordinate system, I want to let the solver know that my angles of my principal stresses, they're stored with respect to those element edge. And those element edges aren't always aligned to the global coordinate system. So we'll turn it on like this, and you can see you get this nice smooth. You can see that tensile stress, that major principal stress in red. And if you zoom in, you can see my minor principal stress is always orthogonal. If I don't have that option set to element edge, you can see I get those same kind of interruptions and change, and those correspond with the element X direction changing. So using this option here helps us transform these results. So it's just another way to visualize your stresses. I think it's really useful, especially with this one where it's kind of tensile dominant. You can see how those tensile forces flow through the structure. All right, last one in the post-processing toolbox is my free body diagrams. Now, free body diagrams are extremely useful. They're really simple, but they do take a lot of practice to get the hang of it. So I'm going to use this button again, reset all of my post-processing. I'm going to turn on my display free bodies, and I'm going to take a quick break right here and show you something in the analysis manager. So let's go to this last page here. I'm going to say manage, edit. We'll go to the very last page of our analysis manager. And what I'm going to do is I'm just going to take a little screenshot of this here. So we can park that to the side. And I'll go back to the toolbox here. All right, so I'm going to create a new free body. I'll park this right here and this right here. All right, so for a free body diagram, you have to choose what type of information you want in that free body diagram. I think this is probably the trickiest part about setting it up. So there's free body contributions. This is the type of data you'll be including in your free body diagram. Now you have to make sure that your output set actually has this information. So by default, you'll get applied load and you'll get constraint force. And that corresponds with applied and reaction. So the most common free body, I think, would be getting a summation of your reaction forces. You grab a cluster of constrained elements, you want to know the total reaction force. Well, you're going to want to make sure that your analysis has requested constraint force, and when you build your free body diagram, that's going to be your free body contribution. If we work our way down the list, next would be equation force, and this corresponds with multi-point reaction. This is for rigid body elements, RBE2s, RBE3s. So if you're going to be generating a free body diagram around a rigid element, you're going to need to request this data before you analyze, and that's going to be your free body contribution. All right, up next we've got peripheral and free body elements. So say we're going to take a little section slice through our structure here. Now if I'm to slice through it right here, I don't have any loads applied directly to those elements. I don't have any constraints. I don't have any rigid elements. I just have my elemental forces. So that's going to be either free body elements or peripheral elements. The two are equal and opposite. And it'll be a little bit easier to see what that is once we move on to the toolbox. But if you want that information, that's the type of free body diagram you're going to be generating, you're going to want to make sure that you turn on force balance. You have to make sure these requests are turned on before you analyze. So this is a common little trick I see with free body diagrams. All right, I had already selected force balance before I analyzed, so I have that information in my model. I'm going to turn on free body elements, and I'm going to use free body only mode. You'll notice the other modes unlock this total force vector. We'll get to that next. Okay, so I have my free body. I've selected my output set. I've selected what sort of contributions. Now I actually have to pick the entities. So I'm going to pick some elements with this tool here. And let's just grab a little selection out of the center of this here. So if I highlight those are my free body elements. And if I zoom in here, you can see each of those elements has a little vector around the outside. So there's not really any out of plane forces. I'm just getting X and Y forces. And I'm getting a vector on each one of the nodes that's connected to neighboring elements. So these are my free body elements. All of the elements around the outside, on the other side of that interface, those are my peripheral elements. So if I choose these free body contributions, I can switch from free body to peripheral. You can see that the directions of the vectors change. If I turn on both, it all disappears because they're equal and opposite forces. They sum to 0. So you're either going to want one or the other, but not both. All right, now what if you want a summation of forces along a certain interface in your model? Right now, if we isolate our free body elements, if I'm to sum up all of the forces around this perimeter, they're going to sum to 0. So to get a total summation vector along some sort of cutting plane, I'm going to have to specify that interface with nodal selection. We need to switch modes here. We're going to have to switch to an interface load. So there's a couple of different ways. You can either build your free body and switch modes, or we can just turn this one off and create a new one. So let's create a new one. This will be called an interface load. And just like before, I'm just going to pick my free body elements. So let's call this interface load. And you can see this unlocks the option for a total force vector. So we'll get a total summation of our forces. Okay, just like before, we select elements. So let me get a little view here. I'll select just a certain bit of elements. Now, it's only really important to grab a single row of elements. If this is my interface here, this line of nodes, I only really need these elements adjacent to that row of nodes. But if I select additional elements, it's not really going to cause any problems. It's not going to change the data. So this line here, this is going to be my interface. So I select elements. I don't have any free bodies showing up. I need to select nodes as well. So I'll come in here, use the Shift key, get a little box select, and select all the nodes along that interface. When I click OK, this pop-up comes. It says Auto Locate Total Summation Vector. So we saw all the nodal vectors, all the forces on the individual nodes. What we have here is our total summation vector. And it's asking me where it's going to place that vector in the model space. What it does by default is it selects the centroid of all those nodes I picked, which is usually a pretty logical place to put it. So I click OK, and there we go. You can see our total vector here in the center and all of our nodal vectors around the outside. You can highlight to see which elements you've selected, which nodes you've selected, and again, you can change what your free body contributions are kind of on the fly from the toolbox. All right, last display mode for the free body diagrams here is the section cut. Now the section cut is actually a little bit easier to use than the interface load, but it gives you the same end product. So again, rather than modifying my existing free body, I'm just going to turn this off and I'll create a new one. Give it a title, section cut. We already know what sort of free body contributions we want. The other thing I'd usually do here is I'll turn off my nodal forces. I don't really want 20, 30, hundreds of tiny little vectors scattered across my model. So I'll usually turn those off unless I specifically want them. And this is going to just give me that one total summation vector. And maybe we want moments as well. We can turn on our moments. And you can see you have the options for components or resultant. Okay, so this one's different. We don't pick nodes and elements. We just pick a plane. So there's different modes for selecting your plane. Usually just go with plane normal. And so what I'll do is I'll say, all right, I want my plane normal direction from this node to this node. So that's going to be more or less normal to the x direction. It automatically selects nodes and elements based on that location. So you can show your free body elements, it selects everything to one side. The nodes, it selects everything along that plane. And then you have some other options like where you want your total summation vector to sit. So right now it's on all along the path. I usually like that nodal centroid there. And you have a little slider. So you can just move this along your model. And I think with something like a side load, it's kind of nice because you can see your shear force remains constant, but as you move further and further from the load, you can see your bending moment grow. Once you have this set up, you can always switch modes, switch back to an interface load or a free body load, and then you selectively choose specific nodes and elements. So this is a nice little addition. All right, so everything above the view properties line, this is all of the real important, the data selection, choosing your contributions, your nodes, your elements. Everything below the view properties line is view settings, how to make it stylized, what size font do you want, what color vectors, how big vectors, how many significant digits. So while I put it on a secondary importance, it's still really nice to be able to control what you're seeing and how it looks. So first one here, nodal markers. You can see that just highlights the nodes that are selected for the interface. You can choose what sort of size they are, make them a little easier to see. Choose colors. There's vector options. So you can choose, do you want to see a value with an exponent, or no labels at all. You can choose your digits, your length. One that I really like to use is this minimum vector magnitude. By default, it's very small, and that gives you vectors even if the components are very, very small, near zero. And I think this is distracting, so I like to remove it from view. So I'll usually increase the minimum vector magnitude. Say I only want to see something above, a tenth of a pound or a tenth of an inch pound. And that's just going to eliminate all the vectors that are smaller than that value. So you can set a limit here. Just be aware if you set it too high, you won't see anything. If I was to choose 110, I'd lose one of my vectors there because it doesn't meet my limit. So you want to set it small, but you can choose to crop out certain small values. And then as you scroll down, you get options for how large you want your vector, what color you want your vector. There's lots of options here. Okay, switching gears. That is the post-processing toolbox. Here's our vectors, our free body diagrams, our section cut. Next thing I'm going to talk about is the data table. Now this is really nice for tabular style data. So I think about it a lot for fasteners. I have beam elements all over my model. I want my axial and my shear force for all those beam elements. I'll just pull them all out, put them in a table, use the data table. It makes it really nice and organized for the engineering report. There's a couple of different ways to add data to the data table. So let's turn off all of our post here. I need to find my data table. It is a dockable pane, just like model info or message or any of these. So if you don't see it, you go to the tools, you click on it here, and it'll pop up somewhere, and you can click and drag, park it wherever you want. A lot of times I park it on my second monitor, but I'll go ahead and put it right here. Now the first thing you need to do is unlock the data table. It's got a lock so you don't accidentally add information to your data table. Once it's unlocked, there's a couple of different ways to add entities to our data table. One of them is the model info tree. So you could go into your elements, say you want to add all of your beam elements to the data table. You select that element type, you click this button up at the top here, and that sends all of those beam elements there. You can do the same for plates. You scroll on down, you can see there they are, solids. So this is a nice method if you want to send an entire type or shape of an element to the data table. If you want to be a bit more selective, I'm going to clear this out and use the selector tool. So the selector tool you'll find on the toolbar. It is right here. And I'm just going to turn this on to elements, and then I can click elements one by one, and you can see they get added to the data table. Now both of these methods put entities in the data table, but it doesn't actually give me output information. So what I'm going to do next is this button here, add output to columns. Now if I'm usually looking at output, I only really want the ID number. Maybe I'll do the property ID as well, but I don't usually need a lot of this data. So I'll go to this button here where you can choose which columns you see. And I like to say update multiple columns. And I'm going to turn all of them off. I'm just going to do ID and maybe property ID. So that kind of cleans out a few of those things that I don't need. Then I'll add output columns. You can choose which output sets you want to include and which output vectors. So let's go with our plate forces, X, Y, shear. We can do bending force, membrane force. And there we go. It spits them out as new columns. Once you get all of the information in here that you want, you can click the little clipboard button. That will allow you to copy it to the clipboard. You can paste it to Excel. Let's try that again. Copy and paste. If you have additional formatting or plotting that you need to do, you can finish that up in Excel. There's another method that I like for the data table. It might save you a few steps. I'm going to go ahead and clear out all of the data in the data table again. And this is under the list menu up top. So if you go to list, output, all of them in this section here are going to dump information to the data table. So a summary will give you some maximum and minimum values for a specific output set. You can see for an output vector, it gives you the minimum value, the maximum value, and the ID numbers where those values are stored. There's also list output results to data table, and this is kind of like using the selector where you would choose specific output vectors and choose specific entities like nodes or elements, and they get plopped out there. So a different path gets you to the same endpoint. It's a really nice way to collect all this information. Now, we've talked about the data table. We've talked about free body diagrams. There's actually a way where you can dump your free body diagrams to the data table. So I'm going to clear this out. We'll go back to the toolbox. We can turn on our free body diagrams here. And let's see here, where is this guy? If you expand the free body menu, you can see you can list them to the message window down here, or you can list them to the data table. When you list a free body to the data table, I'm going to make this a little bit bigger. It lists it by node numbers. So each of these are a node that sits on that interface, on that cutting plane of my free body diagram. For each one of those nodes, it lists the elements that are connected and the forces that those elements contribute to that node. So node 14 has element 249 contributing these forces and moments, element 1301 contributing these forces and moments, and then it gives me a summation of forces on that node from those elements there. So if the graphical representation of your free body diagram isn't enough, you want some hard numbers here for each specific node, you can put it in a data table and collect it that way. All right, our last topic here is the Femap API. So the API is the application programming interface. You can use it to drive Femap in any way you want. You basically don't have to touch the graphic interface if you don't want to. One of the areas where it's really useful and really strong is post-processing. So if you need to export large amounts of data, if you need to modify your view, if you need to create custom output vectors, you can use the Femap API to really help you out with this. So the first two that we're going to look at are sitting in custom tools. So let's take a look here. If you haven't used custom tools, it's a little toolbar here. And if you don't see it, you right click. It is, where does it sit? There it sits in the list. And it's really just an additional menu. And it's just a collection of programs that either users or developers have written and sent into the Femap team and said, hey, I think these are really useful. You might want to include them in the program, or I want to share them with other people. So here they are. So obviously we're going to go to the post-processing menu. The first one I want to take a look at is called List Output to Excel. Now this one kind of shares some of the same territory as the data table. So I'm going to click that. This dialog box is starting to look familiar. You can choose multiple output sets, multiple output vectors. Let's do plate top X, Y shear and plate bottom X, Y shear. You click OK. Now we need to choose which elements we're going to grab information for. Let's do them all around this little hot spot right there. And it kicks it out directly to Excel. You can see the way it organizes it. There's our output set IDs. So we've got output set 4, 5, and 6. Here's our element IDs. And then here's the different output vectors that we've selected. So if you want some hard numbers to put in a table, this is a really quick way to dump it straight to Excel. All right, the next one I want to look at is called the ASME Stress Intensity Calculator. So first of all, let's take a look at some contours here. So I'm going to go to Contour. I'm going to look at my plate top major principal stress, my tensile stress. And now I'm going to find an area with a large discrepancy in top and bottom stresses here. So how about this area right here? You can see this side is very high, the opposite side is very low. But what are the stresses down that membrane there, down the midplane of that element? Membrane stresses are really important for post-processing pressure vessels and ships. A lot of different industries are going to use this, and it's not a default value that Nastran is going to kick out for us. So if you go to Custom Tools, there's this program under Post-Processing called the ASME Stress Intensity Calculator. Let's choose some output sets. Let's do 4, 5, and 6. It's going to run through these output sets, and it's going to give us new output vectors. So I want to know my major principal stress down the membrane of this plate. If you look at our output vectors, here's plate top, here's plate bottom, and now at the very bottom we have plate membrane. So we've generated new output vectors and put them into our output set. So I'll do plate membrane, major principal stress, and we now have these membrane values. You can see they're a little bit lower than my peak surface stress, and that makes sense. Your peak stresses are always going to be on those outside faces. So this is really useful, and it's a good starting point because any of these custom tools you're going to have access to. You can go to the Femap directory, wherever it's stored on your machine. You're going to go to the API folder, and all these folders here, they're going to match up with the different categories of custom tools. So if you need to create your own custom output vector, you might want to start out with this stress intensity calculator, you could see, all right, how does it use plate top X and plate bottom X to generate plate membrane X? I could use that architecture and start building my own custom output vectors. And a lot of the groundwork is already done here. All right, my last API is not one of the custom tools, it's one that I wrote myself, and it is called the output vector switch. So what this does, it's just going to cycle through von Mises, major principal, and minor principal stresses for plates. I included the API in the folder here. You guys will have access to this. Let's talk about how you get to it if it's not in custom tools. So the first thing I'm going to do is right now on the contour I've got a legend cap set from 0 to 30,000. I'm going to turn that off. We're going to switch over to automatic and let it automatically adjust to the highs and lows here. All right, so now I want to access that program. I'm going to go to Tools, Programming, API Programming. From here, I can open up that program. So if I look in this folder here where I've stored the programs, output vector switch, I can hit play, and you can see it's set up to show plate top and plate bottom major principal stresses. It automatically turns on that double-sided planar contours. You hit it again, it switches to our minor principal stress. And I actually had it set up to put your peak compressive stress in red, because your minor principal stress is going to be compressive dominant. I wanted to show that as red. You hit it again, it switches over to von Mises stress. So you can just keep hitting play, and it's going to cycle through these 3 different contours. So I think this is useful, but to open up the programming window and track down this program every time, that's a bit of a hindrance. So what I like to do is build my own custom toolbar button. So I'm going to close this. To build your own custom toolbar buttons, you right-click up here, and you go to Customize. So if you just wanted to add existing buttons to a toolbar, you could go to like File, Save. You could put that on a toolbar here. You can drag them out into the screen here to get rid of them. But if you want to create new buttons from user commands, you go to this tab here, and we're going to go track down that API. So I've got output vector switch. You can see it's in this seminar folder. I'll call it output vector switch. I'm going to add that to my list of user commands, and then I hit close, and this will save that new user command. Then I go back to Customize, and now under Commands, this first category here is user commands. You can see I have output vector switch. So I can just park that on some existing toolbar, and now I've got a button. And I can close Femap, I'll open it back up, it'll be saved on that toolbar. You can do this with any API you want. If there's one in custom tools that you're using frequently and you want to incorporate them into a toolbar, the same process. You go to Customize, you go to User Commands, you give it a name, you track down the directory of the API, and you add it to the list. All right, so there's a lot of APIs that are really useful for post-processing. I would start in custom tools. If you guys work with composites, there's tools that will help you envelope results, skip through plies. There's a lot of potential there. So it's a great place to start. You have the code. You can kind of help yourself see how it works, maybe start tweaking them and building your own programs. If you guys are into programming and post-processing and you guys have questions, feel free to contact us. And I'd also like to show you guys the applied website, because on this website we have all of our past Femap seminars. So here's today's seminar. You can see we've got surface modeling, new features. So it's a great resource for you guys. We're also trying to build up our 5-minute tutorials, so you guys want to Want the quick and dirty rundown on free body diagrams? George has created a 5-minute video there. And you can see I have some on meshing and contact, beam elements. So there's lots of tools to kind of refresh your Femap skills. Anyways, I want to thank you for tuning in. Have a great afternoon, and feel free to get in touch if you guys need any help. Thanks.